Okay, welcome back. So I left you with this idea of thinking about how you might get volume number densities from these column densities, the kind of measurements that come out of spectral line intensities. So if we just go back and look at this image for a moment, just as to focus our attention. So for instance, you see these filamentary structures here in the cloud. So how could you estimate the sort of average density in here, average number density, given these column density measurements on the map? So, in effect, with the column density, you've kind of projected and compressed everything along the line of sight. So to kind of reconstruct that, you're going to have to assume something about how the gas is distributed along our line of sight, as opposed to the plane of the sky here in the map. So if you see perhaps a filamentary structure like this, you might make a reasonable assumption that the width of the filament that we see on the sky is the same as its depth. So basically it looks a bit like a cylinder in an idealized sense, so that you would associate this thickness here with the depth along the line of sight as well. So that would then allow you to, you need to assume a number effectively for the path length through the cloud where you think most of the material is. So you can work out the width of this, and if you assume the depth is the same, you can just divide your column density by that length and turn it into a density. Okay. Similarly here, perhaps if you've got something that looks a bit more spherical or looks circular on the column density map, you might assume therefore it's a sphere and it has the same radius in all directions. And so you could, again, do the same thing. But again, you'd only be working out the average density in that volume. It's probably more dense in the middle than it is around the outside, that kind of thing. So you need to assume that it's, either a constant density within the volume you're considering, and consider that a dimension on here is probably similar to the dimension in the other plane that we can't see along the line of sight. Or you could do more detailed modeling and assume any kind of geometry you like. Okay. So let's have a little think about that line profile function that I introduced into the opacity. So what comes in to that? Again, you can read whole books about this kind of thing, about line broadening. But for I just want to highlight a couple of things here. So at one level, the gas is always moving. So I've referred to molecules here, but again, it could be atoms or ions. But the gas has some finite temperature, and each individual atom or molecule in there is moving around with a characteristic speed. There's a distribution of speeds, obviously, because of the Maxwellian distribution usually. But the fact that the emitting particle is moving because of just the thermal motion of the particles in the gas will cause some that's a Doppler effect. Okay, so the Doppler shift will keep shifting the emitted frequency, nu here, compared to what the frequency would be if the particle was at rest. So nu naught here is the center of the line, the exact difference between those two energy levels that you would theoretically observe for a very narrow line. Okay. So hopefully you recognize this kind of mathematical expression as a Gaussian here. Okay. And this delta nu d here would be the sigma of the Gaussian, if you like. It would be the in a typical sort of Gaussian thing, when you're thinking about using Gaussians or normal distribution for errors, you get a sigma. So that's that number there. If we want to, often you will see our spectra are immediately transformed into velocity space rather than frequency space. Okay, so again, that's just done using the Doppler formula. And that's because, you know, we often immediately want to get insights into the velocity information that the line profile is telling us. And so just be careful here. There's a difference. This is a delta V, so this is a velocity here. And more often than not, we refer to this full width at half maximum of the Gaussian, which I'll explain a little bit more in a moment, rather than the sigma that is normally in the Gaussian. And so you can relate those two things. You can derive that for yourself, the relationship between a sigma, if you like. So this would be the delta V equivalent velocity rather than frequency. So we can relate those two. And this width here is going to be related to the temperature, okay, because this is due to thermal motion. And again, those of you familiar with this area of physics would perhaps recognize this term here as being related to the sound speed in the gas. Okay, so again, the speed of sound in a gas is related to how fast the particles are moving around. So it's a function of temperature. It's also a function of, this would be the mass of the individual atom or molecule involved. K is the Boltzmann constant. Okay, so if we had pure thermal broadening, you can see as the temperature increases, the particles move around faster, and therefore the width of the line would get bigger. Okay. So here's just a diagram to illustrate a Gaussian curve. Okay, so this would be a typical line profile for a line that was coming from a gas that was all the same temperature. And then this full width half maximum here would be determined by that temperature, as well as the mass of the individual particles. If you've got the same temperature and the particles are heavier, then they don't move around as fast. Okay, that's just kinetic energy. So the expression here, full width at half maximum. So the full width, okay, all the way across, not just half the way, and half the maximum. So you just take the peak, the maximum, and you go down by half, down towards 0, and you measure the width there, the full width. And this is the sigma that you normally associate with a Gaussian. And so the full width half max is about 2.235, I think, times the sigma. Okay. So, you know, so quite often in astrophysics, you do see profiles, line profiles of emission lines that, or absorption lines actually, that look like a Gaussian like this. But it's probably quite rare that it's actually purely due to the Doppler broadening of the thermal motion of the molecules. So you will often find that spectral lines that you see are broader than you would calculate from that purely thermal width formula that we just had. So if you know the temperature and the composition of the gas you're looking at, then you know you can always calculate what you expect the thermal width to be, and often you'll find that the lines are broader than that. And this is usually due to additional Doppler shifts above and beyond the thermal motion of the individual atoms or molecules in the gas itself. Okay, so what else? What other motions might be going on? Well, the gas might be turbulent and not static, so that could be just like in an interstellar cloud, you might have a lot of random motions due to turbulent flows within the cloud. So there's no preferred direction necessarily. It's just a turbulent gas because the interstellar medium is very dynamic, and the gas has been stirred up over time. So that would just give, a broader Gaussian, because again, the motions would still be random. It's just that the motions are above and beyond that just due to the thermal motions of the particles. Or you might have, systematic motion of the gas in particular directions. Okay. Now, classic line profiles that you might see are ones that are double peaked. Okay, so instead of a single peak Gaussian, you might have two peaks. This could be due to that the whole cloud that you're looking at is rotating, so that one side is Doppler shifted towards you and the other side is Doppler shifted away from you. So you get a red shift and a blue shift. Or you might have an outflow like in a jet. Okay, so you've got one side of the jet flowing towards you and the other side of the jet flowing away from you. And so if you can pick up emission lines from your jet, then you'll see a red shift and a blue shifted peak. And you can get all other manners of things. You can get inflow as well. So you can get quite complicated line profiles. But that's really a key insight into telling you how the gas is moving, what state it's in. Okay, I just want to return now to this optical depth formula for a moment, because you may have noticed you've got this negative sign here. So what happens if this term N2B21 ends up bigger than N1B12? Okay, so what happens if the stimulated emission process starts to dominate over the normal absorption process of photons? Okay, if that occurred, then this quantity, the optical depth, is going to go negative. Okay, every other thing here being positive. So that doesn't normally happen, because as I mentioned before, in normal sort of thermal equilibrium situations, where the population distribution in an atom or a molecule is just determined by the temperature, then normally N2 is significantly less than N1. But there are situations where N2 can get larger than N1. I'm glossing over some details here as well. And this is what's referred to as a population inversion. And that will lead to what's called maser amplification, or at least in the context of astrophysics, it refers to maser amplification. And that's because normally you have an e to the minus tau factor in your transfer equation, which is describes the reduction in intensity because of the absorption of photons as you go through the medium. Okay, we looked at that in the previous lecture. But if your tau itself has become negative, then that becomes an e to the plus tau factor, if you see what I mean. Okay, so this is, and if the optical depth becomes high, then this leads to an exponential increase in the intensity as you go along the line of sight. So that's like a runaway process then. And this is what masers are all about. And that's going to be the subject of the next lecture. So I'll just leave it at that for a moment. But this is where this idea of negative optical depth and exponential amplification comes from. Okay, so just returning to our sort of radiative transfer formalism one last time here. I haven't mentioned the emissivity at all yet. So you remember that was another term in our derivation of the radiative transfer equation. So there's another way of writing that here. And this is especially true for like an optically thin sort of situation, perhaps when absorption is not significant, but you've got your emitting gas. So if we want to think about how many photons are being emitted per unit volume in the line, then you just need to take the population of the upper level. So obviously the upper level is where the electron is going to be before it drops back down. So the N2 is the appropriate one. And obviously it's going to depend on this rate of spontaneous emission. That's what's giving rise to the photons. Okay, so the faster this rate, then you're going to get more line photons out. This is going to be their energy. This is to it's an isotropic process because the photons are emitted in random directions. So we divide by 4 pi steradians to get this idea of the per unit solid angle, which comes into intensity. And again, we've got this line profile factor because many more photons will be emitted in the center of the line than in the wings of the line. Okay. So you can see that, this is an emissivity. It's an amount of energy per unit volume, per unit time, per unit solid angle, per unit frequency. Okay. And in the simplest cases, you just integrate your emissivity along the path length, and that would be, you can equate that to the intensity that you observe. Okay. So again, this is, especially for optically thin lines, you would basically get a column density out of there because you'd get the integral of n2 ds, and from there, with some assumptions, you derive the total column density of your whatever species was emitting. So that's another way of looking at it. Okay. Okay. Obviously, we can also go back to our local thermodynamic equilibrium assumption, which is another way of writing the emissivity. So it could just be the line opacity times the Planck function. That would also be true in this situation. So you can see there's obviously going to be a relationship between the Einstein A coefficient and the B coefficients, which you can look up if you're interested. So we often have to seriously consider for spectral lines whether we are in this situation where we can assume this concept of local thermodynamic equilibrium. And it's quite a stern test. So it means that each process is balanced by its inverse process. So like, radiative excitation is balanced by radiative de-excitation, collisional excitation balanced by collisional de-excitation, photonization balanced by recombination, et cetera, et cetera, et cetera. Okay, so all of those processes have to be in balance and in equilibrium for this to be true, where we can either put the emissivity equal to opacity times the Planck function, or another way of saying that was that the source function here in the transfer equation is just literally the Planck function. And obviously the Planck function is a function of the temperature of the gas. And so this would be the local temperature if we're just making this assumption. Obviously, the whole universe isn't the same temperature, but if basically the local populations of the electrons in the atom or the ion or the molecule are determined by that local temperature, then this is a good approximation. That is one way to think about it. Okay. So if you think about situations where that might be good, then optically thick situations are good in that respect. If your medium is optically thick, it means you can't see very far. So any photon you do see is only coming from a small distance away. And if it's only coming from a small distance away, the chances are the temperature is similar over there than it was here. So therefore, your little local volume is all the same temperature. You're not getting any information from further away because you can't see through the medium to feel that situation. You're only getting information in and out by the radiation. And so if it's optically thick, then LTE is usually a good approximation. And often for continuum radiation, like we already discussed, like the free process, again, LTE is a good approximation there as well. So, sort of thermal, optically thick conditions are good. But often we have to, we're not able to make this assumption because it can be a very bad assumption. Okay. So when is LTE not a good assumption? Well, often in kind of optically thin situations, especially for spectral lines. And it's because really the radiative rates, which are controlled by the radiation field, are no longer determined by the local radiation field. If your medium is optically thin at the frequency you're considering, you can see a long way away. So you might be able to see other regions which are much hotter. So you could feel a much sort of hotter radiation field, if you like, even though the temperature to you locally is quite different. So that's when things become harder, and you basically have to solve what's called the full statistical equation. So you remember that diagram at the beginning where I showed all those different processes, you know, the radiative processes, the collisional processes. You'd need to, you know, solve those equations to work out your level populations. They're not simply determined by the local temperature anymore. Instead, you can still characterize them by a temperature, which is referred to as the excitation temperature. So what temperature describes the population distribution in your atom, but it doesn't need to be the same as the actual temperature of the gas. Okay, so the gas might be you know, more excited or less excited than the usually more excited than the temperature of the gas, perhaps because you're feeling some sort of hot radiation field from further away. Okay, so again, this might be a little bit tricky, but just have a little think about that in different situations, again, that I've covered in the foundation material. So perhaps which of the following situations do you think LT would be good approximation, and which ones would it be a bad approximation? So just have a think about that in the next 5 minutes of the break, and we'll come back.